Hi, my name is Mrudhula Baskaran. I'm from the École Polytechnique Fédérale de Lausanne, and today I'll be talking to you about the quantification of vortex pinch-off using a robust pressure-based methodology. So vortices are present everywhere in nature. Vortices are used in the dispersion of seeds. For example, we notice the formation of a separated vortex ring atop a dandelion cactus during its flight. We also notice vortex rings that are formed like smoke rings that are ejected from volcanoes, and also other biological organisms use vortex rings for energy-efficient transport in water, such as jellyfish and squid, etc. For studying vortices in the laboratory, we use a vortex generator. Here, two arms compress a polymer bulb, which ejects fluid, and the shear layer that forms inside the cylindrical tube of the generator rolls up into a coherent vortex that's released in the quiescent. We can analyze the vortices that are released by the vortex generator by looking at particle image velocimetry data, and we notice different events in the lifetime of the vortex. Initially, there's vortex growth near the exit of the nozzle of the generator, and the development of a trailing jet right behind the vortex ring. However, eventually, we notice the commencement of pinch-off, where the vortex ring achieves steady-state circulation, and its circulation no longer increases beyond that point. And we note this point when the vortex ring achieves steady-state circulation and compare it to the circulation in the wake, and this time is known as pinch-off, or the formation time. The time of formation of the vortex, or when pinch-off has occurred, is very valuable, especially to devices that produce thrust, many bio-inspired devices, primarily by releasing vortex rings, because pinch-off marks when the flow from the generator no longer is entrained into the vortex ring and marks an end to possible thrust generation. There are many different methods for quantifying when pinch-off has occurred, the first being circulation analysis, where vorticity contours from PIV data are integrated, and the value of circulation in the vortex ring is compared to the circulation in the wake. And although this method is robust, it has some disadvantages. It involves computing or continuing data acquisition well past the predicted time of pinch-off, and to ensure that the vortex has reached steady state. But it also involves identifying the vorticity contours that we can integrate to obtain circulation. An alternative method is the method of Lagrangian coherence structures in the finite time Lyapunov exponent fields. Here we can notice the discontinuation of the positive FTLE field, or the repelling material line, or alternatively we can compute the repelling material line and the attracting material line in the positive and negative finite time Lyapunov exponent fields respectively, and look at the intersections of these two material lines in the fields, and use that to demarcate the vortex, and use that to compute the circulation within the vortex ring, and compare it to that in the wake. Although this method is robust and frame independent, it has some disadvantages. It also involves computing data well past the time of formation, and it can also be computationally expensive. Here we turn to a pressure-based methodology for quantifying pinch-off. A recent algorithm developed by De Bury allows us to obtain instantaneous pressure field measurements from velocity field data. When we look at these pressure fields, we notice very specific pressure features for a vortex. We notice a leading pressure maximum, followed by a low pressure core region that coincides with the vortex core. And immediately behind this low pressure region, we notice another high pressure region, another pressure maximum that we call the trailing pressure maximum. This trailing pressure maximum is significant because it marks the onset of pinch-off. If we look at the pressure signature at the shear layer and plot this over time, we notice the formation of the trailing pressure maximum, but also a low pressure region behind this TPM. This low pressure region coincides with the core of the secondary vortex in the trailing jet. And in a process known as vortex merger, the vorticity from this secondary vortex enters the first low pressure core region. This occurs because of the induced velocity from the first vortex acting on the secondary vortex. Immediately after vortex merger, we notice the formation of a secondary trailing pressure maximum behind behind the secondary, now merged core, and this trailing pressure maximum moves with the vortex ring across the field of view. The fact that the first trailing pressure maximum breaks makes the occurrence of a trailing pressure maximum a sufficient but not necessary condition for pinch-off. In this presentation, we compare vortex merging with some features in the finite time Lyapunov exponent fields, specifically the Lagrangian coherence structures, and show that vortex merging and the features we see in the pressure field can indeed be used robustly to determine when pinch-off has occurred. If we lay the pressure field features and our finite time Lyapunov exponent field side by side, we notice many things. Initially, when the first trailing pressure maximum forms, we notice that this coincides with the connection of the positive and negative FTLE ridges, the repelling and attracting hyperbolic manifold lines, and this coincides with when the first TPM has occurred. Immediately after this, during vortex merging, we notice a stretching of the positive FTLE ridge, and during the stretching, additional vorticity is entrained into the core. After vortex merging, when there's a formation of a secondary trailing pressure maximum, which moves with the core, the FTLE ridges have stopped stretching, are now more compact, and move with the vortex across the field of view. In order to determine if the Lagrangian coherence structures we notice in the FTLE fields were indeed hyperbolic material lines, and not just regions of high shear, we plot the strain rates on these ridges. And from these strain rates, we notice that the strain rates on the repelling ridge, the positive FTLE ridge, are negative, meaning that it is indeed a repelling line. However, during vortex merging, we notice that on this repelling line, there are regions where the strain rate is positive, indicating that additional vorticity moves into the vortex at these regions, at where the shear layer occurs. Immediately after this, most of the ridge becomes immediately negative, has a negative strain rate, showing that eventually vorticity is no longer entrained into the vortex ring. If we look at the cross-sectional area of the vortex ring, plotted from the demarcation of the vortex ring from the FTLE ridges, we notice a general increase in the area of the vortex ring. And this occurs because of the stretching of the ridges during vortex merging, followed by a stretching of the ridges after merging, when the vortex has separated. An interesting plot to see at this point is the eccentricity of the vortex ring over time. The eccentricity calculated from the demarcation of the vortex ring from the FTLE ridges. Initially, we notice an increase in the eccentricity as the FTLE ridges stretch during vortex merging. Immediately after the stretching, we notice a decrease in eccentricity as the ridges stop stretching, and then an increase again in the ridges as they stretch in the opposite direction. We can look at the steady state when certain integral quantities in the vortex reach steady state, such as the circulation, the impulse, and the energy of the vortex ring, and look at when along this eccentricity plot they occur. We notice that the circulation, the first to reach steady state, occurs when the eccentricity is decreasing immediately after it's been stretched for vortex merging, followed by impulse reaching steady state after. And then after the vortex ring has finished its stretching and is now stretching along the other direction, we notice that energy reaches steady state and the vortex ring completely separates from its trailing jet. Now, using this information, we can reconstruct a timeline of important events in the vortex lifetime. Initially, we notice the formation of the leading pressure maximum, followed by a low pressure core region, and then the formation of the first trailing pressure maximum, which coincides with when pinch-off occurs. Immediately after the formation of this trailing pressure maximum, vortex merging commences, and the circulation of the vortex ring reaches steady state. After the circulation reaches steady state, we notice, while the ridges continue stretching, that impulse reaches steady state. The ridges then stop stretching, and we notice the formation of a second trailing pressure maximum, followed by energy reaching steady state and the vortex ring separating entirely from from the trailing jet. From our findings, we realized a lot of things. We show that the first trailing pressure maximum occurs immediately before pinch-off occurs, meaning immediately before the circulation and impulse reach steady state, respectively. And the first trailing pressure maximum also occurs immediately before vortex merging occurs. However, after this, we notice the formation of a second trailing pressure maximum. Together, these two trailing pressure maximums coincide the endpoints of an interval, and during this interval, fundamental things happen for the vortex ring. It achieves steady-state circulation and impulse. This has a lot of implications for devices that rely on vortex production for thrust, because it signifies an end to when additional vorticity supplied by the generator can go into thrust production by directly impacting the vortex ring. And with that, I conclude my talk,